The motivation for this project stems from the idea that people want to use their phones in situations where their hands are occupied and they cannot use traditional touch input. Our goal was to evaluate whether simple foot gestures could be used as a viable alternative to touch input for mobile devices in these situations. The objectives we identified were to investigate how users interact with their phones when their hands are occupied, develop a foot gesture detection prototype, conduct a control user study with this prototype, and present these findings to ultimately evaluate whether or not the foot gestures are a viable solution.
We built a working mobile app that detects foot gestures using the phone's built-in accelerometer. It recognizes 5 gestures based on acceleration thresholds like kicking forward or backward, sliding left or right, or lifting the leg, which you'll see in the demo. To avoid accidental inputs, gesture mode is only activated after 2 quick stomps. The app gives voice and vibrational feedback when a gesture is detected and shows results on the screen in real time. During testing, the phone was strapped to the ankle with a brace to simulate a hands-occupied scenario. This prototype was used in our user study to collect data on performance and usability. To evaluate foot gestures, we conducted a within-subject study with 12 participants comparing foot input to traditional touch. Participants held grocery bags to simulate hands-occupied scenarios and completed tasks like pausing music or answering calls. We measured task time, gesture accuracy, and the number of stomps needed to activate gesture mode. We also gathered usability ratings and NASA TLX workload feedback. For foot input, we used a Wizard of Oz setup where the experimenter observed the mirror screen and triggered outputs using Spotify's remote control. Here are some quick demos of what the task of skipping a song looks like for the 2 conditions. For the foot gesture input, the participant slides their foot to the right and the song skips after the gesture is detected. For the traditional input, the participant puts the bags down, takes the phone out of their pocket, unlocks the phone, skips the song, locks the phone, puts the phone back in their pocket, and picks the bags back up.
We know that before proceeding towards any development, we must be known about users' opinions, needs, and wants. A survey was conducted on different age and gender group people to understand their pain points in accessing their phone interface while both hands are occupied. Also, we wanted to know about their thoughts about using foot gestures instead of using hand. We basically prepared the survey with multiple choice questions along with one numerical input and sent the survey to our classmates, colleagues, family members, and friends. We were cautious enough to avoid unnoticed potential biases, and no personal identifier information was collected during the survey to protect participants' privacy. So finally, we got responses from 41 participants. At first, we tried to learn about the number of situations they face where both of their hands are occupied and they desire to use the phone in that situation. We can see from the table that almost half of the participants sometimes face both hands occupied situations and almost half of the participants want to use their phone in that situations. Participants were asked about the number and the type of tasks they want to perform in a hands-occupied scenario, and 35% participants want to perform at least 2 tasks, and most desired tasks are answering and ending phone call and reading notifications. So we can say that foot gestures could be helpful for them in hand-occupied scenario, but from the pie chart here, we can see that half of the participants are not interested in using foot gestures because most of them think that they may look silly when they use foot gestures in public. Some people think foot gestures may be too complex to perform, they may cause physical discomfort or cause accidental activation or false positive. You can see the details in the bar graph.
These are the results for the comparison between foot input and traditional touch input in our study. Figure A shows that foot input was significantly faster, saving about 75% of the time compared to touch, a result consistent with the original study. In Figure B, participants rated foot input as more useful and satisfying, with both input types being easy to learn and remember, a result also consistent with the original study. Finally, Figure C shows that foot input led to lower physical demand, time pressure, and frustration, even though it required more mental effort, likely due to the novelty of the gestures. Together, these results suggest that foot input is an efficient and ergonomic alternative for hands-occupied scenarios. These are the results for the comparison between our study and the original for foot input. Figure A shows that our foot input was significantly faster, over twice as fast, likely because we used simpler gestures and quicker threshold-based detection instead of the dynamic time warping algorithm. Figure B shows that usability ratings were similar, reinforcing that foot input remains easy to learn, easy to remember, useful, and satisfying even with the differences between the studies. Figure C and D shows comparable gesture accuracy and fewer stomps needed to activate input, suggesting our simpler system is just as reliable. Overall, our findings support that the lightweight approach can still deliver strong performance. This slide compares traditional touch input in our study and the original. Figure A shows that our touch input was significantly faster, cutting the time by over 50%. This is likely due to a simpler, more intuitive interactions like tapping or swiping on the home screen instead of unlocking the phone and drawing shapes. Figure B shows that usability ratings were similar across both studies. Touch input was easy to learn and remember, but still rated lower in usefulness and satisfaction compared to foot input. Overall, our simplified design made touch input more efficient while confirming previous findings about its limitations.
We made some changes to our original plan. Instead of the complex dynamic time warping algorithm, we used a simple threshold based method for gesture detection using the phone's accelerometer. This made our system faster to build and tune and was more practical given our limited timeline and resources. Additionally, we did not fully implement real phone actions for each gesture due to technical and time constraints. Instead, we used a Wizard of Oz setup where gesture detection was real but task responses were triggered manually by the experimenter. This allowed us to run a robust user study despite not having system integration. Both decisions were based on feasibility and early user feedback, which showed limited openness for foot gestures for regular usage. Through this project, we learned that simple foot gestures can be a robust and efficient hands-free input for mobile devices. Our prototype achieved a recognition rate of 93%, and participants were able to complete tasks about 75% faster using foot gestures compared to traditional touch, closely mirroring the original study's results. Despite technical success, we faced real constraints. Most notably, we were unable to fully integrate gesture recognition with actual app actions, so we had to simulate output responses using Wizard of Oz technique. Moreover, the sample size of our study was small and mainly drawn from a similar demographic, which limits how widely we can generalize our results. Finally, openness to foot gestures was mixed. Only a minority said that they'd use it regularly, often citing worries about looking silly, comfort, or accidental triggers in public settings. We feel we achieved the main objectives. We replicated prior study, validated that even a simple prototype can yield fast, accurate results, and we gathered new data on user attitudes. Our technical choices, like using simple thresholding instead of dynamic time warping, work just as well for our use case and were practically more feasible within project constraints. On the other hand, time constraints and technology limits prevented us from demonstrating a fully deployable real-world system. While we are encouraged by the prototype's performance, it is clear that for hands-free input to be widely adopted, future solutions must prioritize not just reliability or speed, but also comfort, privacy, and context of use. Our project highlights promising directions as well as persistent barriers for practical adoption. Thank you.